How to write the electron configuration of an atom. Okay, to write the electron configuration of an atom, we first need to understand orbitals, shells, and energy levels. Let's look at this example. Carbon has an atomic number of 6, a mass number of 12, and 6 electrons. Its electron configuration is 1s2 2s2 2p2. Each number in the configuration represents the shell number or energy level surrounding the nucleus. The letters S and P refer to subshells or orbitals. Carbon has electrons filled in first and second energy level. The S subshell contains only one orbital. P subshell consists of 3 p orbitals. Each orbital can hold a maximum of 2 electrons, meaning the p subshell can hold up to 6 electrons in total. In general, shells are numbered starting from 1. Shells, or energy levels, are composed of subshells, which can be of type S, P, D, or F. Each subshell contains a specific number of orbitals. 1 orbital for S, 3 orbital for P, 5 for D, and 7 for F. Each orbital holds 2 electrons. The maximum number of electrons that can occupy each type of subshell is 2 electrons for S, 6 electrons for P, 10 electrons for D, and 14 electrons for F. Therefore, the total number of electrons a shell can accommodate depends on the types of subshells it contains. Hope now you have general idea. 3 rules need to be followed to write the electron configuration. First one is Aufbau principle. Electrons fill orbitals starting from the lowest energy level to higher ones. This will show you the filling order. Starting from 1s2 2s2 3s2 3p6, something strange happens. The 4s2 orbital is written before the 3d10 orbital because the 3d orbital has higher energy than the 4s orbital. A similar thing happens between the 5s and 4d orbitals. To understand the energy state of each orbital, you can follow the chart given. The second rule is Hund's rule. Electrons fill orbitals singly first, with parallel spins, before pairing up. Think of it like passengers choosing empty bus seats before sitting next to someone. Let's take the oxygen electron configuration as an example. Pauli exclusion principle. Each orbital can hold a maximum of 2 electrons with opposite spins. Let's take a look at the electron configuration of the helium atom. It is 1s2. The 2 electrons are filled with opposite spins. Denoted as minus and plus half based on quantum number. Let's look at a couple of examples. Hydrogen has 1 electron, so its configuration is 1s1. Helium has 2 electrons. It should be 1s2. Nitrogen has 7 electrons. 1s2, 2s2, 2p3. Fluorine has 9 electrons. 1s2, 2s2, 2p5. You can also write configurations using noble gas notation. For example, helium covers the first shell, and the rest of the electrons can be written beyond that. Then, we can complete the outermost shell. Generally, we use an 18 groups of atoms, like argon, to simplify notation. Next, scandium is a D-block element and belongs to the 3D group. It has 21 electrons. One S2, 2 S2, 2p6, 3s2, 4s2, 3d1. Next is titanium, which has 22 electrons. 1 S2, 2 S2, 2p6, 3s2, 4s2, 3d2. Vanadium is the 23rd element. For the rest of the atoms, I am going to write the electron configuration using argon as the core. For vanadium, argon 4s 2, 3d 3. Chromium has 24 electrons. Its expected configuration would be argon 4s 2 3d4, but this is incorrect. The correct and more stable configuration is argon 4s1, 3d5. One electron from the 4s orbital is donated to the 3d orbital to achieve a more stable, half-filled d subshell. After that, we can follow the same order to fill the rest of the atoms up to the 28th element. Copper, which has 29 electrons, prefers a more stable configuration like chromium. Electron configuration is argon 4s1 3d10. For the zinc atom, the next electron goes into the 4s orbital, so it's argon 4s2 3d10